All right. I think we left off on Friday looking at this reaction. We talked about using dionyl chloride. We talked about using PBr3. And Friday, we left off talking about this reaction using HX, right? Well, X is a halogen, and it is either iodine, chlorine, or bromine. And we also talked about the quality of the leaving group, how to tell it. And we're going to talk more about that when we do substitution and elimination. But the way you determine how good a leaving group is you look at the pKa of the conjugate acid of that leaving group. So, and that sounds like a lot, but it's really you take the leaving group and you add a proton to it. That's the conjugate acid. So we talked about that. And in this case, water is a better leaving group than the hydroxyl group. And all of these reactions that we talked about in terms of converting oxygen into a better leaving group. So that first step, that proton transfer, is to get you to the hydronium ion, at which point you lose the leaving group. And then you generate this carbocation intermediate. So that's where we stopped on Friday. And then the final step is here, right? I have it, I wrote it out kind of separately, even though the carbocation, I showed it here, it's the same here. I just wrote it in a different step. So that carbocation plus iodine is going to get me to my product, right? So I'm going to get just a tack here. At the carbocation to give me my alkyl halide. Right, and don't forget, that's what we're talking about, how to make alkyl halides from alcohol. So we got 3 methods so far. Right, this method, again, I talked about this, is specific to secondary and tertiary alcohols. There's a reason for that. And the reason is carbocation intermediate. All right, can somebody tell me, as far as carbocations are concerned, right, a carbon with a positive charge, what's the trend for their stability? Like, what is the most stable carbocation that you can make, and what's the least stable carbocation that you can make? Anybody?
Are you talking about the 3, 2, 1 thing?
Yes, that's exactly what I'm talking about.
So I think 3 is the most stable and 1 is the least stable.
Okay, good. So for your carbocation intermediates, I'm just going to write this in here. What's today? The 12th. Wow. So for carbocation stability, right, a tertiary is greater than a secondary, which is greater than a primary, which is greater than methyl. Right, it's the opposite when you're dealing with carbanions, which are negatively charged carbons. Right, so for this reaction, you can think about this in terms of carbocation stability. Right, a tertiary alcohol is going to react faster because the carbocation intermediate is more stable. The secondary is going to react a little bit slower because the intermediate is a little less stable, so on and so forth. So we look at a reaction like this. I'll cut it out. Right, we look at something like this. Right, what type of alcohol is that, first of all? And then the other part we'll discuss after we figure out the type of alcohol we're dealing with. In other words, is it primary? Is it secondary? Is it tertiary? I think I gave y'all that description when we first started. good. This is a primary alcohol. Now, using HCl with that primary alcohol, what would you expect to happen to the rate of the reaction? What would you expect to happen to the rate?
Is it concerted?
Say again, you're a little bit.
Concerted?
No, that's the. I'm not saying that's wrong. That's the mechanism though. But okay, so when we talk about the rate, we're talking about how fast or how slow a reaction is, right? So if you took a primary alcohol and reacted it with HCl, let's just go through the steps, right? What's the first step?
The OH is attacked by chlorine.
No, the first, let's go back up to here. What was the first step up here? Right, the alcohol is actually doing the attacking. So it's the oxygen and the alcohol that's attacking the acid, right, and doing that proton transfer. You're right that something's going to happen between them, but it's the other way around. The chlorine is not going to be involved until the very last step when it's time to do the substitution. But if we look right here, right, what's going to happen here is this is going to do, so I can erase that without erasing the image. Yes. All right, that's going to do that, right? And then you end up doing a proton transfer. I may be off by a carbon in the product, but don't worry about it. What's important is what the intermediate looks like. All right, and then this is this intermediate plus what? Chlorine. Right? The fact that it's a primary the fact that it's a primary carbon, now we got a problem, right? Because with this method and the mechanism, what's supposed to happen next? What happened in this reaction up here? Once you made the hydronium ion, what was the next thing that happened?
The leaving group?
Leaving group left, right?
Yeah.
Okay. So the reason I asked about the rate is because this is a primary alcohol. And if the mechanism stays the same and the leaving group leaves, right, I'm going to be left with a primary carbocation plus that. Is that good or bad? And this would be the SN1 route, right? Because with the SN1, the leaving group leaves first. With the SN2, everything all happens at once. Is that good or bad? Given what we know from right here, let me just copy it and bring it down. What we know from right here, that one of the worst types of carbocations is a primary.
So I'm guessing it's bad then.
It's horrible, right? So if that's why I said on Friday, certain tools work on certain reactions and certain tools don't. So for this reaction, right, the HX route for a primary alcohol is bad because you're going to form a primary carbocation. right? That primary carbocation is going to slow that reaction down. So when I asked about the rate, I asked that question on purpose. So the rate is going to slow down significantly, right? With a primary alcohol and this method. Right now, there is an alternate pathway that may open up or that may happen. And that is what? What do you think? What's the other substitution method that could happen? Right, we have one method where the leaving group leaves first and makes a carbocation. What's the other method? Could it go concerted where it's just simply attacks here like that, all in one step? Could that happen, do you think? Yes, no, maybe?
I'm sorry, my audio cut out. What did you say?
I was asking if you could potentially go through the other method where you have a direct attack by the chlorine. Remember, one method, you lose the leaving group, and then the nucleophile comes in, that's SN1, SN2. The nucleophile just attacks and forces the leaving group out. I think we talked about that on Friday.
Like the carbocation intermediate method?
There's no intermediate
Oh, yeah.
if it goes through SN2. Right, remember one of them is stepwise and one is concerted. Didn't we talk about that Friday? Somewhat, touched it at least.
Yes, you did.
So one is stepwise, one is concerted. So the concerted pathway would be faster, but more than likely, this reaction is just going to be a brick, right? Because of the reagents, the HCl, and it's going to you're going to have this carbocation intermediate that will not want to form, so the reaction will probably slow down to nothing. That's why I asked about the reaction rate. All right, questions about this method, right? It works best on secondary, tertiary alcohols. It's not as good on primary alcohols. And if it does work for primary, it does not go through the SN1 pathway. It can't.
I have a small question, I guess. So let's say if you ask that on an exam, would you want to see both options or?
Yeah, you can show both, because in chemistry, whenever we propose a mechanism, it's just plausible. There's always like some other way to think about a mechanism happening. So yeah, you can show both.
Okay, thank you.
Yeah, great question. And anytime on an exam for a question similar to this or whatever, if I ask you to propose a mechanism, right, that means that you need to show the steps and the arrows, how each intermediate is formed and stuff like that. So yeah, you could show that. But the way a question like this would be written, maybe I'll give you a primary and say, show an alternate pathway. You understand what I'm saying? By which this method could work on a primary alcohol or something like that, if that makes sense.
Yeah, it does. Thank you.
Yeah, no problem. All right. Other questions? That was a great question, by the way. All right. Let's see if we can apply this. Right. So let's go down, and if you have the handout, which I've posted multiple times, also told you where to find it on Blackboard. Let's go through and work through some of these examples, and then maybe we'll have time to start a little bromination. And really, that's going to be the extent of the exam, because the exam is Friday. So we'll have, but we're still having class. So the exam will be posted on Friday. You can take it, but you have until Sunday to take it. So let's work through some of these examples. It says, first example says, give the correct reagents to convert the given start materials into the products shown. So what is that asking? Because most of, how do I put this? Most of the time, when we have a deficiency in a course or we have a deficiency on an exam, the first step to problem solving is understanding what the problem is asking you. So when it says the correct reagents, what does that mean? What is a reagent?
What you're adding into it.
What you're adding into it, what you're adding together. So we have one of our reagents already, the alcohol. The topic is converting alcohols to alkyl halides. We have the product, right? And where we see now that alcohol has been converted into a bromine. So now we need to look at what type of alcohol that is. What is it? Is it primary? Is it secondary? Is it tertiary? That's going to determine what method, what we put in this box, right? The type of alcohol is going to determine what goes in that box. Because again, we got 3 methods. One of them is suited better for tertiary. The other 2 can be used for primary and secondary. So what type of alcohol is this? So you have to ask, you're asking these questions in your mind while you solving these problems so that you'll know exactly what method to apply. All right, anybody, what type of alcohol is that? What the way we determine that is we look at the carbon where the alcohol is and count how many carbons are attached to it.
Tertiary.
Come on, don't be scared.
Is it tertiary?
It's tertiary. Be confident. You can see that there's 3 carbons attached to that carbonyl. Is that right?
Yeah.
Yeah. Just be confident. You know what you know and know what you don't know. But this you know, because we've seen it more than once. All right. So that's a tertiary alcohol. Now, of our 3 methods, which one works best with tertiary alcohols?
Carbocation.
Say it again. Yeah, the one that goes through the carbocation intermediate. Yes, you're right. Okay, so now what reagents are used with that method? That's the question. Because you're right. I agree with you 1000%. But what reagents does that method use?
Acid.
Some type of acid, good. And look at the product.
Alcohol.
Mhm.
Water, right?
Yeah, water is a side product, yes. But look at the product. What acid would I use? Would I use HI? Would I use HCl? Would I use HBr? Would I use H? You understand what I'm saying? We need to know what acid to use because the product is specific, right? The alcohol didn't just get turned into a random halogen. It's a bromine. So
Is this
what?
with the halogen?
Yes. So what acid am I using? H what?
Well, I guess it's HBr.
HBr. Right. That's what I'm using. I just put the bond there. I mean, you don't have to show that when you write out HBr. You don't have to show that sigma bond, but I wrote it. But yeah, that's what you're using. This method the HX method is specific for tertiary alcohols, right? We know that. We looked at 3 methods and the mechanism for each method. All right, let's go to, oh, this is a good one, B. Let's look at B. Okay, what type of alcohol is that? That's the first question. Once we know that, we know what method to use. Now I'll even write the methods up here. We had thionyl chloride. We said that was primary and secondary. We had PBr3. This is primary, secondary, and then we had HX for tertiary. Those are 3 methods. Turn the volume down. All right. So look at reaction B and tell me which one of those 3 methods you would use. It's a secondary alcohol, so you're not going to use HX, right? So now you're limited to PBr3 or thionyl chloride, SOCl2.
So it's the thionyl chloride.
Thionyl chloride, right? Because your alcohol has been converted into what? A chlorine. Is that right? I mean, that's part of the method is which halogen I need. So if I want a chlorine, then I'm going to use thionyl chloride. All right. Now let's look at the second question. We can go back and apply that to the first question as well. It says determine the type of substitution, SN1 or SN2. And then it says a hint, you can use the product stereochemistry in some cases. I'm going to explain that part. All right. But let's go back to the first reaction. Somebody mentioned, I don't know who it was because I can't see who was speaking. But somebody mentioned that in that first reaction, excuse me, that there's a carbocation intermediate. Is that right? I can't remember who that was that said that. But you were right. So if the reaction goes through a carbocation intermediate, which substitution mechanism is taking place? All right, let me refresh you. Where did I talk about that? Here. All right, if the leaving group leaves first, it's SN1. You can see the mechanism. The leaving group right here is leaving. You get a carbocation intermediate, and then the nucleophile attacks it. If it's SN2, everything happens all at once. The nucleophile comes in. You can see that right here, and it forces the leaving group out. That's how the substitution happens. So SN1 is stepwise. SN2 is concerted. All right, so there are no intermediates for that particular substitution step. So let's go back to here and we can answer this question. If we know that the first reaction goes through a carbocation intermediate, which mechanism is working there? Is it SN1 or SN2?
Is it SN? Because I'm looking at it and it seems like it leaves first. So is it SN1?
Yes. But see, here's the thing though. You're right about that. But it's a tertiary alcohol, right? And you're using HX. So we know the mechanism for that. So we know the leaving group leaves first. We got to convert it into a better leaving group in that first step, just like we did here. And then the next step, that's what happens. The leaving group leaves. And then in the third step, the nucleophile attacks. So you're right. But see, with that method, with HX, we know for a fact that it goes through a carbocation intermediate. So we can say definitively that it's going to be SN1, especially if it's on a tertiary carbon. So you're right. All right. What about the second one? What do you think? This one is a little bit trickier, but I'll explain it. I'm actually going to cut this out to explain it. All right, anybody? Uh-oh. Let me try to do that. All right. What do you think? When we did the thionyl chloride mechanism Friday, the substitution step, did we say it was SN1 or SN2? Anybody remember?
SN2.
We said it was SN2. Excellent. All right. We're going to go through the mechanism again so I can show it, but what do you notice about the product? Right? We got a chiral center here. Is that right? Isn't that a chiral center?
Yes.
What's the configuration? Test question. I need some Jeopardy music. And how do we determine the configuration? And which way is the hydrogen going?
Okay. The hydrogen's in the front.
Is it in the front?
Oh wait, is it? I'm not. I think so.
Wait. The OH is on the wedge. That means it's doing what? It's coming out.
Okay, so I was answering for the OH. The hydrogen's going to the vac.
Okay. I agree. So what does that mean now? Do we need to reverse it or anything like that once we prioritize it?
No.
No.
Because the hydrogen's already in the vac.
All right, so oxygen is 1. You agree with that? Hydrogen is 4. It's the lowest priority group. Out of those 2 carbons right here and right here, which one do you think is 2? And which one is 3?
The one to the left is the 2.
Good. And then that's 3. I agree with that. So is that clockwise, counterclockwise? What is it?
It's counterclockwise. Is wait, yes.
Yeah, you're right. All right. What about over here? Chlorine is 1. Now the hydrogen is here on the front. That's 4. This is still 2. That's still 3. So what do we got? That's counterclockwise again, isn't it? But what's the but?
The hydrogen's on the wedge.
All right, exactly. So we need to reverse it. So now is what over here? It's R. Anybody not catch that? All right, good. All right, now here's the question. This is a very, it's kind of a loaded question, but what's the mechanism? That's the other part. It asks for the mechanism. It says determine the type of substitution mechanism. Right, we already determined the reagents. Now we need to figure out if this was SN1 or SN2. One of the ways to tell if a SN2 reaction has happened is to look for what we call inversion of stereochemistry. Right, if stereochemistry gets inverted, in other words, R goes to S or S goes to R, then you know it's SN2. That's a guarantee. That's like 99% guaranteed. There are some cases with the SN1 mechanism where you'll see inversion, but it's rare. It's really rare. Right, so that's a dead giveaway for SN2. All right, so let's go through take this reaction and let's go through the mechanism. Put the electrons in here. Carbon plus S. Come on, Russell, tighten up. All right, what's the first step? The only reason I'm doing this is because I want to show you why the stereochemistry is inverted. That's it. All right, so what's the first step?
The proton transfer.
And not in this case.
It's different.
Not in this case. Not in this case. In this case, remember, this is polarized. Go ahead.
This is the reaction with the thionyl chloride.
Yes, yes. So the first step is the attack of the alcohol on thionyl chloride. Right, so that's going to give me an intermediate It looks something like this. And keep in mind, the reaction itself has multiple steps. When we say stepwise or concerted in relation to the substitution, right? That's just that one particular step, whether it's SN2 or SN1, because truth be told, like 99% of your reactions happen in multiple steps, right? But the substitution step that we're talking about, that's what we say, if it's stepwise or concerted. And if it's stepwise, it's SN1. If it's concerted, it's SN2, right? But a lot of reactions have multiple steps, but the particular step we care about is the substitution part. So this is going to be here. I'll gotta zoom in on that. I'll keep my stereochemistry. So this is OH. You know what? Hold up. I missed a step because this is also with pyridine. So I'm gonna take this H off. Let me fix this right quick because we're supposed to have a proton. You're right. Who was that? Was that you, Asia? That said proton transfer?
Yeah.
I apologize to you because you are absolutely right. The first step is a proton transfer with pyridine. So thank you for that. My apologies. So that's that and then that, right? So then up here, this step is now the oxygen is negative. You're right. Thank you for that. And if I made you second guess yourself, I apologize. All right, so that's that. That's going to attack the thionyl chloride and get me to here. Now what? What's the next step?
The loss of chlorine.
Good, good, excellent. That's the elimination step. So I'm going to eliminate chlorine, which eventually will become my nucleophile. This is O, S double bond O, Cl plus Cl minus. That's negative. All right. Now here's the part where the stereochemistry gets inverted, right? Because when the chlorine attacks, all right, I want you to notice. So there's a hydrogen going back. Let me put that back in. I want you to notice if the OH is on a wedge, and if this is concerted in an SN2 mechanism, the nucleophile is always going to attack from the opposite side of where your leaving group is. So if the leaving group is on a wedge, the chlorine is going to come from the back side. And let me see if I can draw this in kind of 3D. So this is and this is going to be a transition state. This is the O, S double bond O, Cl. This is the H. And then on either side, you have the ring here, and you have another carbon, an ethyl group there. So let me move that over. That's gonna be cramped up. I draw this neater now. So this is S double bond O Cl. Right, so it's like we turned it to the side so we can see it from the side. So the chlorine is actually coming in from here. It's going to come in from the opposite side of where that leaving group is to kick it out. So this is why the stereochemistry gets reversed. So inversion occurs because the leaving group always, and for SN2 mechanism, the leaving group always attacks, I'm sorry, the nucleophile always attacks from the opposite side of where your leaving group is. Right, so that's why you see that inversion. So when that happens, that's going to give me the product that looks like this, right? Where the chlorine is now facing back instead of so it's that. Right? That, but the inversion, again, the reason the inversion happens is because the chlorine has to come opposite of where the leaving group is.
So what was on the wedge? The oxygen the
Yes,
whole time?
yes, yes. And the only reason the chlorine had to come in from the back is because the oxygen was already facing the front. If the oxygen was on the dash, then the chlorine would come from the front and kick the oxygen out from the other side. But the oxygen was, the stereo center was already set. Is that right? If you look here, it's already set. And it doesn't change until that carbon gets attacked by that chlorine nucleophile. All right. Does that answer your question?
Yeah.
Mm-hmm. All right. Let's go back to, let's do C. What do you think? What did we use? First of all, what reagents? And second, what mechanism? Based on what we know about B, can we now look at C and say the mechanism right away? Can you see that the OH is on a dash and then the bromine is now on a wedge on the other side?
Yeah, that's inversion.
Yes. So what's the mechanism?
SN2.
So SN2 mechanism, good. What would you use to convert that alcohol into that alkyl halide?
I think that's the PBR.
Good. PBr3. Right? Because I want to turn this into bromine. And of my three methods, it's the PBr3 that actually gives me the option to turn OH into bromine. And again, it's a SN2 type mechanism. And you can propose that by, if you go through the mechanism, you'll see the intermediate. I can draw it here. The intermediate would look like this. Right, and this is what bromine is going to attack. But bromine is going to attack it from the, in this case, from the front side, not the back side, because the oxygen is already facing back. Right, so it'll attack from the opposite side. All right, let's see if we can run through these last two, and then we're going to go back. The last thing we're going to do before we quit is talk about the reaction energy diagram. I'll give you a little bit of refresher on that from part one. All right, somebody hit me with the next to last reaction. Anybody? I got a primary alcohol and I converted it into a primary alkyl halide. What did I use to make that make the OH into a chlorine? It's a primary alcohol. That's the difference in what that tells me what method to use.
It's OCl.
Good. Thionyl chloride. All right. What about the last one? Tertiary alcohol. I converted it into a tertiary alkyl halide.
That's the HX.
Good. And what would X be in this case?
Bromine.
Yeah, good. So this will be HBr. Good. All right, so it asks us to draw a reaction energy diagram for both A and C. All right, so let's do that. So when you write out a reaction energy diagram, I'm just going to do this here, right? It's always here, right? This is time. I think I showed you this already one in a previous lecture. This is energy, right? And you always start with the reactants going to products, right? At the top, there's a transition state. If it's more than one step, then it's reactants going to intermediate, going to product, right? If there are multiple intermediates, then you're going to have multiple steps. So let's take A because we can run through that one pretty quickly. So let's take it. It is it's OH. All right. Plus is HBr. Is that right? Yes. HBr. Right. First step is what? We got 2 minutes. Is it proton transfer? Is that right?
Yeah, so is this is concerted, right?
No, it's not. It's actually
Oh.
stepwise.
Oh, I think you just said that. Sorry.
Yeah, that's okay. So now what happens once I turn that oxygen, that hydroxyl into a water? What's the next step?
Is there a proton transfer?
Well, that's the first step. The second step, that's to get to the next step where I lose my leaving group and and make a carbocation intermediate. So now this intermediate is what's going to get attacked by bromine.
Okay. I think the way I wrote it in my notes is really confusing.
What do you have a question about it? We can answer it right quick.
I just got everything happening
All
at
at
one
once.
time, I think. Yeah.
Yeah. No, this is definitely one of those reaction mechanisms that has multiple intermediates. So the first step is proton transfer, right, to get here. Second step, loss of leaving group. And then the third step, nucleophilic attack. Question is, what does the energy diagram look like for that? So the first step is going to be fast, really fast. Right, so this is the proton transfer step. And that's going to lead to the intermediate. We'll call it A. Intermediate A. The next step, loss of leaving group, is slow. So we're going to show that with a higher activation energy. That's going to lead to the carbocation, which is, we'll call it B. So that's going to be intermediate B. And then the final step, nucleophilic attack, is fast relative to the other, leaving group leaving step. And that'll give us the product. Right, so the energy diagram for this reaction will look like that, where it's 3 humps. Every hump represents a step. So the proton transfer is a step that leads you to an intermediate. Loss of leaving group is a step that leads you to another intermediate, which is the carbocation. And then the final reaction or the final step in the mechanism is the attack of bromine, right? So that leads you to your product. So the energy diagram is representative of the overall reaction. You have to show every step. The energy, as far as the activation energy, right? The energy to get to the transition state in each step, that's relative because we don't know that. It's just estimated. All right, we got to stop here. Any questions before we log out? I'm 2 minutes over.